ketones today. There are a couple more reactions to talk about for aldehydes and ketones, and then we'll start talking about carboxylic acids and their derivatives. And no calculus. Otherwise, I won't be here. I don't do calculus. Or rather, I should say, I can't do calculus. Anyways, so I don't remember the numbers. What number was the last reaction?
The winning reaction.
What
number
10?
Yeah.
Okay. Let's
the
talk
Witten.
about the next reaction also of aldehydes and ketones, and this is called, it's called Baeyer-Villiger. I don't know if it's Villiger or Villiger, I'm not 100% sure in its pronunciation. Oxidation reaction of aldehydes and ketones. Oh, I forgot one more. Shoot, that's not listed there. Why is it not listed there? I'm talking to myself. Okay. Does it make sense to do this before? Okay, well, I wrote it and you guys wrote it, so we should mess with it. Okay, Baeyer-Villiger oxidation is an oxidation reaction where, so aldehydes or ketones, even ketones do undergo this reaction. The oxidizing agent is something you've seen before. You guys remember seeing this before?
MCPBA.
In what context have we seen it before?
Epoxides.
Exactly, right? It's giving us an oxygen atom to make epoxides from alkenes in that sense. Here also it's going to give us an oxygen atom to convert an aldehyde or a ketone into either carboxylic acid or an ester. So an oxygen atom, one of the oxygen, do you guys remember what category of compounds MCPBA is? What kind of a compound is MCPBA? What does it stand for?
A benzoic acid.
Not quite.
Meta.
What does P stand for then? So, okay, what does M stand for?
Meta.
Meta,
Chloro.
chloro,
Peroxybenzoic acid.
perbenzoic acid. It's a
Metachloroperbenzoic acid.
It's a per acid, which means it's got chlorine in the meta position, but the benzoic acid is not just a benzoic acid, it's a perbenzoic acid. The per bond is the oxygen-oxygen single bond, that's called the PER, per bond. And one of the oxygens from there is inserted right here to either convert aldehyde into a carboxylic acid or ketones into esters directly. So for example, let me give you examples and then I'll add a little bit more detail to that. No mechanism needed. We don't need to think about mechanism here. But for example, if you start out with, I don't want to do that just yet. Okay, fine. Let's say if we have pent-3-one, right? Symmetrical, choosing symmetrical for a reason here. And you reacted with MCPBA. Oxygen, one oxygen from the oxidizing agent inserts itself into one of those bonds. So what would that become? Anybody? If an oxygen atom inserts itself into one of these C-C bonds, either here or there, because it's symmetrical, doesn't matter, what would the ketone become?
An ester.
Agreed, right? It's an oxidation reaction because you added an oxygen atom. Where is this oxygen coming from? It's coming from MCPBA. It's the extra oxygen from the per acid. We're not looking into the mechanism. Make sense, everybody? On the other hand, if it were an aldehyde, what would this become?
You wrote a carboxylic.
Oh, thank you so much. Thank you. What will it become? The oxygen from here, the oxygen from there will insert itself right there. So this would become a
Carboxylic acid.
carboxylic acid. Everybody okay? Now there are other ways of converting aldehydes into carboxylic acid. Can you tell me another way that you know of that I could convert aldehyde into carboxylic acid, not using this method but a different,
Oxidation.
using what?
N2 and C
Sodium dichromate, basically a
with
strong
H2S,
oxidizing.
H2H.
With H plus, H2SO4, right?
Mhm.
Or even for that matter, CrO3 with sulfuric acid, it's the same thing, right? The point is strong oxidizing agents can also be used to convert aldehydes into carboxylic acids, and that's another way. This reaction, Baeyer-Villiger oxidation reaction, is more useful for ketones because so far we have not been able to oxidize ketones. This allows us to oxidize ketones into esters. That's where they're more useful. Does that sound okay, everybody?
Mm-hmm.
So can you tell me what would be the product if cyclopentanone is reacted with MCPDA?
Well, there should be an O
When?
in that corner.
Wanna draw it?
I
Sometimes
don't
it's
know.
easier to draw than to, right?
I'm just thinking,
That's
but
okay.
I'm not sure.
That's fine, we'll figure it out. Oh, then you lost a carbon.
Oh, true.
You have the right idea. You have, no, don't do that. Don't do that.
Oxygen cannot
You
make
have a right idea, Kumar. Your original idea is correct. But now how do we change the, what is that?
I don't know, I just
What,
invented.
just draw what you had originally. The first thing you drew, draw that, because you were correct. But now let's change the rest of the structure to count for the number of carbons there are. How many carbons should, there you go. That's it. Exactly. Everybody agrees? Oh, thank you. Everybody okay? Now, so far I've chosen symmetrical ketones, but then what if it's an unsymmetrical ketone where you could get different products depending on where the oxygen goes. If the oxygen goes here, you get one product, but if the oxygen goes on that bond, you get a different product. So there is a selectivity here in terms of where the oxygen would go. We call this a migratory aptitude because if you look at the mechanism, there's an actual movement, migration of one part of this molecule to the other side. We're not looking at the mechanism. So the point is the selectivity is for hydrogen greater than tertiary, greater than secondary, greater than, where does phenyl come? Yeah, secondary and phenyl are almost the same. Phenyl greater than primary, greater than CH3. So what does that mean? It means that of the two possible products, let's draw out both products. Okay, let's just draw both and then decide which one would be major. So if the oxygen comes here, you get that product. Does that sound okay? But on the other hand, if the oxygen goes to the other side, that. Now, which will be major product? If you consider that.
Should we consider how do you say?
What's that carbon?
Steric.
Primary or secondary or
Oh.
tertiary or?
secondary
Secondary.
carbon.
What about this carbon?
Tertiary.
So where would oxygen prefer to insert itself between? So this would be your major product. Make sense? Everyone okay?
Mm-hmm.
Yeah? Okay, let's look at a couple more examples. Same reagent, just give me the major product.
Word, but won't say it.
Mm.
Hmm?
What's the difference between primary and CH2?
Primary would be CH2. So,
Oh.
this is, sorry, I see where you're coming from. I would call this primary, this would be secondary.
Oh.
My mistake, but the major product's still the same. So this is CH3. So that's just the CH.
So CH3 would be,
No, the same rule,
oh, okay.
same order. So which one will be the major product? Where would oxygen prefer to be?
Between the C double bond O and the benzene.
Do you guys agree?
Yeah.
It would prefer to insert in this bond. So what's the product?
That one.
Major product, agreed?
Yes.
Everybody okay?
Mm-hmm.
What about the next one? Which bond would oxygen prefer to insert itself in? The hydrogen. So hydrogen is the most,
Oh, the most.
right?
Yep.
So what would be the major product?
The carboxylic acid.
Carboxylic acid, exactly. What about here? Where would the oxygen prefer to insert itself?
Tertiary.
Over there?
Yeah.
With this bond right here?
Yes.
Right there? So do you all agree? Yes. 1, 2, 3. Becomes the major.
1, 2.
This is Baeyer-Villiger oxidation, and again, the main use for Baeyer-Villiger oxidation is to convert ketones into esters directly. Otherwise, you have to do a lot of indirect stuff. Plus, when ketones become esters, notice how number of carbons is not changing. That's again a very unique feature of this reaction.
Now comes the next question. I
Yes.
see second degree and phenol are about the same.
Then you'll get both products. Yes, exactly. You won't have selectivity, you'll just get almost, again, expectation. Practically what happens, you can only say when you do the reaction, but expectation is you will get about the same quantities of both.
So for Baeyer-Villiger oxidation,
Mhm.
ketones into
Esters.
esters and aldehydes into carboxylic acid, right?
Yeah. Everybody okay? Okay, cool. The next reaction, let's call it reaction number 12, is something that most textbooks do in a couple of chapters. But this textbook is actually doing it here, so let's just cover it now. Excuse me, I'll erase this. So,
It's number 12, right?
Yeah, number 12.
Yeah. So, conjugate nucleophilic addition reaction. Now, before we talk about that reaction, I want to ask you, because you've done it before, you've seen it before. Can you tell me, giving, let's use this, is this an aldehyde or a ketone or neither?
Ketone.
Do you all agree?
Mhm.
But there is something unique about this structure. What is that?
Diene.
It's not a diene,
Not
but I
diene.
think what you're trying to say is,
It's an enone.
it is not an enone. Well, okay, it is an enone, but also what specific kind of enone? Because this is also an enone, but not the same thing.
Conjugated.
Conjugated enone. It's a conjugated system. Do you all agree with that? We've studied conjugated systems
Yep.
before, right? And I think that's what you were thinking about when you said diene earlier. But the point is, it's conjugated. The two double bonds are in conjugation with each other. Is everybody okay with that? So I want to ask you, because we've seen this before, if I were doing the following reaction, I'm going to do it in step by step. So first I'm going to react it with, let's just say R MgX. Where would R go?
The C double bond O.
Okay, R will go to the C, isn't that right?
Mm-hmm.
What does that create?
Alkoxide there are.
In this case, yeah, of course, it creates, and the R is here, and minus charge, isn't that right?
Mm-hmm.
And what happens next? After that, what do?
Then you acid to protonate.
We add an acid to protonate, so where does the acid go?
To oxygen.
So, the point I'm trying to make, which is why I'm using all of these different colors, is where did the actual addition happen?
Wouldn't it also happen in the,
Where did the actual addition happen in the steps shown here,
Added across the C double bond O.
which is called 1,2 addition? I think we've talked about last quarter about direct addition and conjugate addition, isn't that right? Last quarter when we looked at dienes, conjugated dienes, the answer is yes, we did talk about, remember, thermodynamic product and kinetic product and all of that stuff. The point is, this is a direct product because R and H went across that pi bond. Do you guys see that?
Mm-hmm.
Grignards do this. Grignards only do 1,2 addition. Grignards, because they're very strong nucleophiles, they only do 1,2 addition. The R will go to the carbon of the C double bond O, proton goes to the O, you get the product that we've all learned about so far. Everybody okay?
just
Yes.
1, 2?
Yes, 1,2.
Where's the 1 and where's the 2?
1, 2. So again, last quarter, if you remember when we were numbering the conjugated systems, I would call this start 1, 2, 3, 4.
Okay.
So
Oh.
it's added 1, 2 across one pi bond.
Okay.
Everybody okay?
Mm-hmm.
However, there are quite a lot of nucleophiles that actually do conjugate addition. So just to show you that, and again, I'm not using an example yet, we will, but right now I just want you to notice how the product will be different. So step number 1, the nucleophile comes in, but instead of going to carbon of the C double bond O, it goes to carbon at the end of conjugation, carbon 4. Then what happens to the pi bond here?
It breaks
And what?
and it becomes a carbon.
Moves to the, no, moves. Why? Because there's resonance, guys.
Of
rest.
course.
It's all resin, that's why it's conjugated, because it's resonance, delocalized.
Mm-hmm.
What does that create? What is the intermediate once that happens?
The pi bond is shifted over.
The pi bond has shifted over, and where is the nucleophile now? Is the nucleophile on the carbon? No, it's
It's on the
fourth
end carbon.
position, carbon 4. If you look at the numbering that we had, 1, 2, 3, 4, right? So the nucleophile went to the end of the conjugation. That's carbon 4 of the conjugated system, and yep, double bond shifted over, and O has a minus charge. Agreed?
Oh,
And then comes in
the acid.
H3O plus or H plus or whatever. Where would that go?
It would attach to the oxygen.
So please, again, I'm doing all these coloring businesses because I want you to notice, where did everything go? So where is the nucleophile?
On the end.
4th position, right?
Mm-hmm.
Where is the proton?
On the oxygen.
On the 1 position,
Mhm.
oxygen. So if we were using numbering, that was 1, 2 addition. What would you
1,
call
4.
this?
1,
Exactly.
4.
This is 1, 4 addition. That is a direct addition. 1, 2 is a direct addition. Nucleophile to the carbon, proton to the oxygen, direct on one pi bond. This is conjugate addition. Agreed? Yes?
Yep.
Okay, now, before we go further though, what does this look like to you? The conjugate addition product, what is that? Look, what is it?
An enol.
It's enol. And what do we already know about enols?
Very unstable.
Very
And do what?
A tautomer.
They
Tautomers.
tautomerize. What would the actual product be?
Keto.
No, go ahead, throw it out. What would the actual product be? Enols are not stable. They very quickly tautomerize to the keto form. This is an enol. But enols don't survive too much, typically speaking. They quickly tautomerize, and we have written the tautomerism mechanism that everybody should know. In presence of an acid, a tautomerism happens, acid catalyzed. What's the final product?
The CO.
Mm-hmm.
It's a keto, yeah.
And the ketone.
Ketone.
So the final product will not be the one for enol, although it is created first, obviously. Yes, it is created first, but then this quickly tautomerizes to the keto form and gives us the product. So please notice the difference between the two approaches. Certain nucleophiles, no matter what, just do direct addition, such as Grignards. Grignards do not ever do conjugate addition because they're very strong nucleophiles. But then there are certain nucleophiles that actually, if they have an option, they will go conjugate, not direct. So, just as an idea, since I just said Grignards only do direct, Grignards never do conjugate, which are the nucleophiles that you are likely to come across that do conjugate additions instead of direct addition? So the most common one that you will probably come across is amines. When amines add, because they are weaker nucleophiles, they actually do conjugate addition. And I'll give you some examples. They do conjugate additions if that's an option. The other more common one that you will also come across, and I don't know if you've seen these before. Have we seen these before? Dialkyl cuprates.
Somewhere.
Lithium dialkyl, I can't remember. Huh?
When we learn Grignard.
Yeah.
Did we talk about that? Okay,
Yeah,
so these are
I don't
also
remember the
weaker. And again, I want to remind everybody, the actual nucleophile is here. So this is basically a lithium counterion supporting a dialkyl cuprate anion. The actual nucleophile, the R, comes from here, one of them. It's a much weaker nucleophilic reagent than Grignards because if you look at the periodic table, magnesium is way more metallic than copper is. Copper is a weaker metal compared to magnesium.
Gilman's reagent?
Yes, that is Gilman's reagent, absolutely. So this bond is less polar than the RMG bond. Basically, R is in Grignards, it's way more R in Grignards is way more electron rich, therefore a way more stronger nucleophile, really strong nucleophile because of the metallicity of magnesium compared to that guy. The point is, what I need you to keep in mind, Grignards only do direct. Grignards never do conjugate addition. But cuprates, they go conjugate. They don't do direct. If they have an option, that is.
Did you call it cuprate?
Cuprate. Okay, so this is, of course, it's called Gilman's reagent. And its name is lithium dialkyl cuprate. Oh, I can't spell. Cuprate. Okay, did we talk about how to make dialkyl cuprate?
We made it from an alkyl halide.
Very good. And then? Okay, so
I don't
let's
think
review
so.
that very quickly so that you have it fresh in your minds. Where is my pen? How do we make dialkyl cuprates? Yes, you're absolutely right. We make it from alkyl halides, but in two different steps. First, you react it with two equivalents of lithium, converts that into lithium, organolithium compound. Of course, lithium halide is also created. Who cares? That's a byproduct. The RLI, the organolithium compound, is then reacted with cuprous halide. 2-to-1 ratio. Two equivalents of this, one, or I can say half an equivalent, because you want twice of that compared to this. That gives us R2CuLi. So it all comes from alkyl halide, absolutely.
That's negative Li, oh yeah, okay.
Sorry, what?
No, negative
Minus,
lithium
meaning,
and
okay. That just basically
halogen.
means you're also creating this, but that's a byproduct. Okay. So
Oh.
you remove it, get rid of it, because it's a byproduct. Yes? Okay? Okay, let's look at a couple of examples of this, and then we can go to carboxylic acids.
So it's only those two that do the?
For now,
Okay.
yeah, and these are the common ones. I mean, are there others? There are plenty others.
So
It has to do with nucleophilic strength.
if we see any others,
That's why I only included these two. You're not going to see, not at this stage. Okay, so let's try these out. So for example, if you have if I'm reacting this with what would you say?
we want two products,
Sorry?
it'd be the direct products.
Actually, you should say that's not going to work.
Mm-hmm.
Isn't that right?
Yeah.
Why would you say that? You should look at me and say, Smita, that's not going to work. What are you doing? Why?
Oh, because it's an acid inside the grain yard, they use up its stuff.
You cannot
We
have
can't.
Grignard.
You
Oh,
You can't have
oh.
Grignard. No, because you got to pay attention.
can't have
Okay.
You cannot
Grignards and
have
acid.
Grignard, anything with anything protic. Can't. Now it's okay.
Can't have Grignards and acid.
Please, go ahead. How would the products be different? Or what would the major products be? sorry. Please. Oh, what are you asking there, Sunita?
A lot of things.
Yeah.
What do you want there? Okay. Okay.
Two different questions, is that what it is?
Yeah, the top one is separate, this is separate. Yeah, I didn't leave enough space. Does anybody
But-
have a,
Oh,
no,
no.
go ahead, what?
No, but HBR comes from the,
No, below the line is a separate question. Above the line is a separate, different question. Not sure what are you thinking, Mark?
like, what do we react with HBR?
That's what I need you to tell me.
Oh, so you need the
Yes.
answer over here.
Whatever
Oh.
is missing, you
Oh, I got
give
it,
me.
I got it.
Are you feeling better?
Yeah,
No pain? Or you still have
I
pain?
still do.
You gotta go check it out. Because that can be serious, right?
Yeah, that's why I don't wanna go. I don't wanna
I
hear it.
understand. I understand where you're coming from. But
I'm like, if it's gonna happen, just let me have it. Yeah.
you got a life forward. Go get it checked out. Is that, Carter, is
Okay.
that, oh, no, is that a double bond there?
Yeah, that's a double bond.
Okay, cool. Can I just draw it a little,
Yes.
bigger? I'm just gonna draw it a little bigger. So you're saying that's a double bond,
Mhm.
and, right?
Mhm.
Okay.
Oh, yeah, 'cause it definitely stayed.
Where? Oh, you're talking. Are you sure? HBr does not brominate
right. I was
an
thinking-
alkane.
It brominates an alkene.
It can brominate an alkene, sure. I think you were okay everywhere else, Dash. It was just that last, with the first. You didn't have to erase the rest. Other things were good.
Phenylpropyl.
It's only your first starting point.
2-phenylpropyl.
Yes. Everything else was good.
2-phenylpropyl.
How about the next one? I mean, the
How
one
about
on the
number
top right.
9? OH. How do we replace an OH?
Wasn't that just, green? No?
We're taking out an OH for a phenyl.
First of all, you can't use Grignard if there's OH somewhere.
Yeah.
Remember, you can't have
Grignard,
Grignard with proton. Secondly-
Grignard's does not substitute
Secondly, Grignard would go here,
with protic
but that's
stuff.
still there.
Yeah.
Can't be.
ETOH.
Oh, yeah.
I think leaving makes sense. So if you just put the acetone first.
Yeah. Where do you work? It's similar. Where you,
While Camilla is writing that, do we all agree with these two products? Are we
Yeah.
all okay with these two? Everybody?
Yeah.
Grignard does direct, that goes conjugate instead.
Or is the,
Oh, the dial.
Oh, I was thinking S8.
What happened?
No,
I
that,
don't know.
Oh, wait. We can do essays.
Okay, I got the OH steps. It's OH in presence of an acid. And then,
Am I right?
hold on.
Okay.
That's a great. I think that's it. That's what we need.
That's it?
Yeah. And then,
And butyllithium.
all you need is H2O at the end to bring it back. That's all we need.
yeah,
That's just it?
Yeah.
We're adding the phenol.
Well, I mean, like, that's
No, for that set.
protected.
Oh, okay, okay.
There's no double step.
I'm kind of lost in the 0.5.
Half equivalent, meaning if you
One.
take
I was thinking
half.
add the phenol.
So if I have, let's say, I'm just, if I have 2 moles of this, I need 1 mole of it. If I have 1 mole of this, I need half of it.
So what does that do?
Stoichiometry. So, because I need, in order to make this,
Make that a good leading.
in order to make this, how many R's do we need?
2,
How many CUs do we need?
1.
So how many of this will I need to get 2 R's? Would you need 2 of those?
Yes,
And how many of
So we make
this will I need?
and then.
Okay.
1.
1.
Uh-huh.
So that's a 2:1 ratio, right? Or 1:half ratio. If I take 2 of this, I need 1 of that.
Oh, okay.
If I take 4 of this, I need 2 of it.
Oh, okay.
If I take 1 of this, I need half.
Half.
It's basically that ratio.
So it's 1.
It's a stoichiometry basically.
Oh, okay.
So if I'm, because the way I wrote that, I was starting with 1, 1, 1, so then copper has to be half.
Okay. No, thank you.
Yeah.
No, wait.
H2S
Concentrated.
concentrated.
Hydrosulfuric acid, that's right. Dehydrates.
It makes it into it.
Yeah, so it actually gets rid of the OH and the H.
And then what am I using?
Okay, and then that makes double bond. And then from there, we want the 1,4, so you have to do phenyl, 2 phenols. Wait. Oh, that's right, yeah.
So you put 2 fat lines.
Yeah. And then CuLi. And then H3O at the end, and bring the OH.
Exactly my question.
I'm like looking, I'm like, well, I don't think we.
Why do you need step 1?
We were originally thinking of protonating the OH to make a leading group.
Yeah, so
Yeah,
But then we realized we didn't need to
we
do
were,
that
we were
anymore.
going a different step here, and then we figured it out, the true step.
but as soon as you'll add this, wouldn't that,
Yeah,
so why do we need step 1? The answer is.
we don't.
We don't.
Yeah.
We don't need to protect it. You can dehydrate, in fact, that dehydration will, no, you don't need that, because you need to put a proton on the O minus and the mechanism, so,
That would be
but,
step 3.
yeah. But in fact, a dehydration of an aldehyde or a ketone, of an alcohol in presence of an aldehyde or a ketone goes fast because you get a conjugated system, way more stable. So, no, you're fine, you don't need to protect that. 1, 2, 3, done. Now, do you guys agree with this? Do we need to go over them or we are okay?
I would.
Concentrated sulfuric.
What is, what's gonna happen in step 1?
Concentrated sulfuric acid takes out an equivalent of water.
So what is that going to create?
An alkene.
And
An
this
alkene
case-
al.
Yes, in this case, a conjugated one,
A
Yeah.
conjugated
Ah.
alkyl.
right? You get that
Oh.
1,4 system.
I
Now
got
you
it.
have a conjugated system.
Okay.
So now if you do the Gilman's reagent, that goes to the 4th position and gives you the.
Got it. Okay, perfect.
Is this one okay?
Mm-hmm.
Okay, cool.
2-phenylpropylamine.
So, this is chapter aldehydes, ketones, number I do not remember.
Chapter
Let's
19.
go to carboxylic acids and derivatives of carboxylic acids. So, what is a carboxylic acid, anybody?
RC double bond O single bond OH.
So, a carboxylic acid is anything that has this functional group. Isn't that right?
Mm-hmm.
That's a carboxyl functional group. Carboxyl functional group from carboxylic acids. This carbon is not a carbonyl carbon. It's not. By the way, please, can you take a look at the C double bond O carbon and tell me in aldehydes or ketones, and tell me if you think these carbons are the same as that carbon.
No,
Are the
they're
blue
not.
circled carbon the same as the red circled carbons?
No.
No, why? What's the difference? One of them is more, the resonance they both have because you got pi bonds and lone pairs and all
Same.
that stuff. One of them is more oxidized than the other.
Mm-hmm.
Which one is more oxidized than the other?
Carboxylic acid.
Absolutely. This is the highest oxidation state of carbon in organic chemistry because higher oxidized than that is carbon dioxide gas, which is not organic. It's not considered organic. The C double bond O carbon in carboxylic acids has the highest oxidation state possible for any organic compound. So this is not a carbonyl carbon. Carbonyl carbon is aldehydes, ketones is carbonyl carbon. This is called a carboxyl carbon. The highest oxidation state possible. That is the reason why carboxylic acids have the highest priority when it comes to naming. In IUPAC naming systems, carboxylic acids have the highest priority because that carbon has the highest oxidation state. Okay?
Mm-hmm.
Now, what are the derivatives of carboxylic acids? Which compounds are considered to be derivatives of carboxylic acids? By the way, what does the word derivative mean? Anybody? You're saying it, you're just not loud enough for me to hear. Comes from, derived from, that's basically it. All the compounds that are created from carboxylic acids are the derivatives of carboxylic acids. Which families are the ones that are considered to be derivatives of carboxylic acids? Please tell me, what is this? Yes, that's one of them. But which one is this? I'm going in order.
Hello.
Acid halide.
Acid halides. This is not alkyl halides. That's not a ketone. This is an acid halide. What is this?
Ester? No. Oh.
Acid anhydride.
Exactly, acid anhydrides. Basically, two acids condensed together. We'll look at the details as we go through one at a time. That's an acid anhydride. This linkage, very, very common in biochem molecules. Very common. Then comes, what is this family?
Esters.
Esters, also very common in biochem. And what are these?
That's an amine.
Amines, very common in biochem. What are proteins? What are really proteins?
Amines. Amides.
What are your saccharides, sugars, complex sugars and all? What are fatty acids? Esters.
Mm-hmm.
So these three categories, and carboxylic acids too actually, these four categories are very relevant biochemically speaking, because most biochemical, the biomolecules, what we call them, are basically either these, these, or amines, if you really think about it, nothing more than that. Let's talk about amides. How many types of amides possible?
Primary, secondary,
Good.
tertiary.
What is a primary amide?
It's a name.
Primary amide.
What's a primary amide? What's on the nitrogen? Two hydrogens. Just like primary amines. Primary amines is RNH2. Two hydrogens on the nitrogen. Exactly the same for amides. What's the secondary amide then? How many hydrogens on the nitrogen?
One.
Exactly like the secondary amine. What's a tertiary amide?
All ours.
No hydrogens on that nitrogen.
Just like a tertiary amine. Exactly. So amides can be primary, secondary, tertiary, depending on how many hydrogens are on the nitrogen. Everybody okay? What is the hybridization state of the carboxyl carbon in all of these compounds? What's the hybridization state of those carbons?
sp2.
Absolutely. What should be the shape? What should be the bond
Trigonal.
angle?
Trigonal
Absolutely.
planar.
Exactly. Everybody okay? Cool. Could you please pass these around? Please take one, pass these around.
Oh, good. Good. Mark?
Okay, let's talk about naming these different families of compounds. So that's why I thought I'll make a copy of these instead of writing and drawing everything on the board, which can get tedious. We're going to name each of these different, one more, shoot, I forgot. Derivatives, acid halides, anhydrides, esters, amides, right?
Yep.
There's one more. Please write that down at the bottom. And that is, please tell me, what is this family called?
Nitrile.
Nitriles. The cyano group, nitriles. Those are also considered to be derivatives of carboxylic acids. So we will learn how to name each of these families one step at a time, but
There's no CO?
no, exactly, but it comes from there and goes back to that. That's why. You're right, there's no CO. Okay, let's start with carboxylic acid naming, and then we'll go to the other families one at a time. So in IUPAC system, carboxylic acids are called alk and oic acids. So this is one word, and then the word acid, right? What does alk mean?
Parent chain.
What about it?
Number of
Number of what?
number of carbons in the parent chain.
So, what is the parent here? The parent will be, carboxylic acids is the highest priority group for naming, period, of everything. So the parent must contain, longest chain of carbons that contains the carboxylic acid group has to contain. Would you expect carboxylic acid group to be in the middle of the chain or the ends of the chain?
Ends.
Right, if you
Just
look at
like
the
our-
structure, it has to be at the end. So therefore, your numbering will always start from there. That's carbon 1. Has to. Everybody okay? And then of course you number in the longest direction. What does AN tell us?
sp3 hybridized carbons.
So all other carbons in the parent are sp3 hybridized. Agreed?
Mhm.
What if there were a carbon-carbon double bond in the parent?
In.
What if there were a carbon-carbon triple bond in the parent?
Ein.
What if there were more than one of ene or ein?
Dein.
Sure. Okay, what else?
Dia.
Alka.
Alka.
Remember?
Alkadine.
Alka triene or diene, alka tetraene or whatever it is, then you add an A there, right? Everybody okay? What's the maximum number of oic acid groups, carboxylic acid groups
Two.
possible on one parent?
Two.
Two.
Two, because they have to be on the end.
Like
So
out
if
of-
there were two, what changes will you make here? If there were two carboxylic acids, what will you do here?
Dioic.
Dioic with the numbers. Even though it's kind of intuitive, you still give the numbers in that case. If there were two, you must give the position number. 1,7-dioic acid, for example. What other change do we make if there were two of those?
And E.
And E there. Do you guys remember those
And
rules?
even.
None of those things change. It's the same thing. Everybody okay? What if though the carboxylic acid was on a ring?
Psych.
Then just like aldehydes, remember how we name aldehydes on a ring?
Mhm.
Then they are called cyclo, alk, and E with the E is there. But then you call it carboxylic acid. And I'll give you examples. So why did I do that? I have no idea why I did that.
What did you do?
I put a space between them. I don't know why I did that. I have no idea. Exactly. So just like for aldehydes, they are cycloalkane carb aldehyde. If a aldehyde is off a ring, similarly, if a carboxylic acid is off a ring, it's cycloalkane carboxylic acid. But there is one cycloalkane, one carboxylic acid on a ring which is not named like this. It has its own special name. By the way, guys, please tell me this, because in the middle of third quarter Ochem, if I see this and it's called cyclohexane, that's not okay. Third quarter Ochem, middle of third quarter Ochem, this is not cyclohexane.
It's
What is it?
benzene.
So by now that should not be called cyclohexane, whatever. There is one carboxylic acid on a benzene that has its own special name. What is that? Does anybody remember?
Benzoic acid.
That has its own special name. This is not cyclohexane carboxylic acid. That is benzoic acid. Everybody okay? Let's just try these carboxylic acids first, then we'll go to the other. You have the first, I think the second page on your handout. Let's take a look at that. Oh, okay, yeah. Please, second page, on those, can I see what's on the second page? Is it the same as this? Yeah. Let's go ahead and try it out. What do you guys think? I made copies so you don't have to draw. You can spend more time on naming. So first, what's the parent?
The carboxylic acid. The long.
But how many? What? Which?
1, 2, 3, 4, 5, 6.
So where is the numbering starting from? That's your 1. Period. And then in the long direction. So do you agree? 1, 2, 3, 4, 5, 6, 7? Okay, cool. Now, even again, I know I'm saying this sounds like she's nagging us again, but again, middle of third quarter, Ochem, shouldn't there be stereochemistry?
Yes, I was
Yes.
Then
gonna
why
say
are
it.
we forgetting?
No, I was not.
I'm not saying you. I'm saying you didn't. But again, I'm just saying generally. Why are we forgetting that, guys? So let's start with this. What is that? Stereochem.
Easy.
Is it E or which one? Carter, do you guys agree? Everybody agrees? It's E? Are you sure?
I don't know, I haven't checked.
One.
Priority 1, priority 2.
Yeah.
Priority 1, priority 2, so
E.
Okay, now let's start with the naming part. So what's the alk? Oh no, groups first, I'm so sorry. Groups first.
2-chloro.
2, 4 what?
2-chloro.
2 chloro, I'm so sorry, I thought you said 2, 4. 2 chloro,
5.
5 what? Methyl. Then what? Now comes the alk, right?
2.
What's the alk here?
Hept.
Hept. Is there an ene or ein?
Ene.
So then you gotta give the position
2.
of the ene. Where is the ene?
2.
2.
2 ene. Right? Are we ready for the parent now, or do we have anything more to put in there?
I think it.
Well, why
We're not
didn't we
ready
put
for
the
parent?
the parent already?
Right. No, I mean the last part of it,
Oh,
the primary functional group. So how are you going to complete it?
Enoic acid.
That's it. The 1 is implied because there's only one oic acid, so it has to be on 1, so you don't have to verify. Does that make sense, everybody? Okay, let's.
Can put it, right?
Sure you can, but you won't see it most. When you see the names, you won't see it written. Okay, let's look at the next one, guys. Once again, please tell me what is the parent. Which one is the next one?
Is it next one down or next one across?
Yeah, that's what the question I was asking. What do you want to do first?
Across.
Okay, let's do the one across then. Okay, what's the parent?
Non-ein.
Is it non? Okay, cool. So where do I start numbering the parent from?
The carboxylic acid.
Perfect. 1, 2, 3, 4, 5, 6, 7, 8, 9. Agreed?
Mm-hmm.
Okay. Stereochemistry?
No.
No. Groups?
Methoxy.
Methox.
So tell me.
Oh, what's 38? Methyl.
What comes first, methoxy or methyl?
Methoxy.
Alphabetical. So 5-methoxy. And then?
8 methyl.
And then? Now the parent, right?
Mm-hmm.
So let's start.
Non-free ein.
Non-3-ein.
Inoic acid.
Only one oic, so. Do you agree? Everybody. Okay, let's look at the next one. That's a cyclic one. Why don't you have the structure in front of you? I don't have to draw it. Can you just tell me the name? What do you guys think?
2-oxo.
2-oxo. The keto group as a group is an oxo group. And then?
Oxocycloheptane.
No, it's oct, right? Did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8.
6, 7,
Eight.
8. Yep. Cyclooctane.
But cyclooctane, and then? 1, 2, 3, 4.
1,4-dicarboxylic acid.
Yes, 1,4-dicarboxylic acid. Because the carboxylic acid part, there are 2 of. For the di ones, you have to give positions.
do you have these up in Canvas?
No.
Can I have another copy so I can upload it for
Can,
Jane?
let's,
Yeah, okay.
it's probably there somewhere. I know, probably there are some extras around. For Jane?
Yeah.
Or anybody? Yeah, I'm sure. I'll find it.
Okay.
Okay, let's look at the next one, guys. How would we name this guy?
HO.
The next one,
Mm-hmm.
3 aminyl.
Amino. Do you all, no, 3? Are you sure it's 3? What is it?
1, 2, 3, 4.
4. Do you guys agree? 4 amino. Okay, then what?
5 methyl.
What?
No, not 5. Again, 1, 2, 3, 4,
But
5,
who's
6.
going to come first? Methyl or what's the OH called as a group?
Hydroxy.
Oh, hydroxy.
Hydroxy, no.
3 hydroxy.
Is it 3?
Yep.
So you have, no, is it 3?
1, 2, 3. I want to go that.
Okay, what, okay, and then what's methyl
6
then?
methyl.
Okay, and then what?
Benzaldehyde.
No,
Benzoic acid.
it's benzoic
Oh, I'm
acid.
sorry.
Not
Aldehyde, I'm sorry.
aldehyde. But is this correct, guys?
Probably not.
No, the only reason is numbering has to be lowest combination. You numbered it in the anti-clockwise direction, right?
Mm-hmm.
What about if we numbered it in the clockwise direction? Would this will still say 4. What would hydroxy become?
5.
And what will methoxy? Did I say methoxy? It's not
Hydroxy.
methoxy. No. This is not methoxy. This is methyl, right?
Methyl, yeah. 6 methyl.
Maybe 2.
That would be 2. So which is a better combination? Is it
2, 4, 5.
so this one?
Yes.
So you do have to pick the smallest combination of numbers. You got a number from the other side.
Yeah.
4 amino, 5 hydroxy. 2
Everybody
methyl
okay?
benzoic acid.
Okay, let's look at the next one. Oh, did somebody say wait?
No, I'm telling myself.
Oh,
So you call it amino, not aminyl. No.
no, it's amino. But Mar, did you spell it this way or did you spell it as with an I-O?
No, I was doing it with an IL.
Oh, no, it's not amino, it's amino. Yeah, I got it. Okay, what about the next one, guys? So what's our parent?
1, 2, 3, 4, 5. A pentane.
Where are we going to number from?
From the bottom.
Why the bottom one and not the top one?
Lowest combination.
Mm-hmm. 2, 2, 3, 3.
Oh, that will be 3, 3. Okay, good, sorry, yeah. So 1, 2, 3, 4, 5, am I right?
Mm-hmm.
Okay. Group, is there stereochem?
No.
No.
Okay. Groups,
2 ethyl. 2, 3, 3 trimethyl. Pent dicarboxylic.
Pentane.
Pentane. 1, 5 dicarboxylic acid.
that's only for cyclic ones.
Dioic acid.
Oh, this is not a cyclic one. Because for cyclic carboxylic acid, it's cycloalkane carboxylic acid. That's why we did it here because it was a cyclic acid. What happened? Yes, we do. Sorry, we do. But do you see that, Camilla?
Yes.
Yeah. This is just a dioic acid because it's not cyclic. Yes, we do need that E because there are 2 of those. Absolutely. Is this okay with everybody? Next one. Ooh. How many of you remember when we started learning IUPAC nomenclature in 261?
Mm-hmm.
And look what it is now.
Mm-hmm.
So that's what growth looks like, right?
Mm-hmm.
Anyways, so what is this going to be?
There is stereochemistry.
There is stereochemistry coming from what?
3 and
Carbon.
5.
Carbon 5.
Oh,
I
the
think
double
that-
bonds?
Yeah.
Okay.
It might be E.
I don't know, which one? Let's start with parent first. Let's start with parent. What's the parent?
Starting from the left, one.
Okay,
A hep,
I mean,
a heptene.
7.
2, 3, 4, 5,
No,
6.
you missed one.
You
Yes.
missed one.
5, 6, 7. Agreed?
Yes.
Mhm.
Okay, let's start with stereochem.
So number 3 would be a cis.
We don't say cis.
I'm sorry, it's Z.
Is that a Z? Is that 3 is a trans?
Oh, that's
So
right.
H are
Yeah,
on
no,
opposite
I don't know
sides.
why I was.
That's
Yeah,
okay.
I was.
So do you agree 3E?
Yes. And 5.
Is that, do you all agree 5
Yes.
is Z?
Yes.
Stereochemistry done. Now the groups, please. 5-ethoxy.
7 phenol.
So shouldn't we count this? Shouldn't it be 8?
No.
No, he.
That's exactly what my reaction is when I'm grading. Like, what? What's wrong? What's wrong? Let's think about it. Why is that not correct?
The carbon is not part of the chain.
Exactly. A carbon can either belong to this or belong to that. It can't belong to both. Phenyl includes that carbon already, so that can't be part of the parent then.
Mhm.
It can't be this and that. It has to be one or the other, and this carbon is part of the benzene ring. So it cannot be part of that.
I'm just thinking about something crazy that,
What is the crazy part?
like, from 6, couldn't that be a benzyl?
But again,
I mean, I
you
would
gotta
do it
find
that
the
way.
longest. It would be
I would
benzyl
do
if
it.
there was something else longer than 7.
Uh-huh.
Then it would be benzyl, but you gotta pick the biggest, longest chain.
It's only, yeah, I don't know, comes out of.
Because it stops there.
If it was in the middle,
If, let's say, again, hypothetically
Yeah.
speaking, let's say there was another group that went
then
more,
yeah,
then your parent is that.
benzyl.
And then that has to
Okay.
be the.
Yeah.
Okay, coming back, yeah, so 5-ethoxy what?
7 phenol.
Phenyl.
Hepta free 5 diene.
Slow down. Hep what? What?
Hepta
Hepta?
free 5 diene.
3, 5, oops,
Use commas there, not dashes.
there we go. Diene.
Dienoic acid.
Oh, there's only one oic acid. Do you guys agree?
Mhm.
Okay, quickly, let's draw the structures of some names that are given on that. Please go
2,4-dichloro cyclobutane carboxylic acid. Okay. Two, 4. Epoxy paint pen.
Is it?
2, 3, 4, 5. Deck. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. Where's mine?
You're saying 4 and I'm thinking 3.
Yeah.
Why does it say 1-hydroxy if the benzoic acid is on 1? Is it talking about the?
Ha 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 ha, thank you, good, okay, that's great questions.
I thought it was maybe just referring to the.
No, it's a mistake, you're right, it is a mistake. How can it be 1-hydroxy if benzoic acid is 1? which is a rule. So let's make it something else. 2 is an ene, so you can't. That'll make it an enol. Enols are not stable, so it can't be 2 or 3. 5 it can't be, 4 can't be, so 5 can't be. You can make it 6. What's the parent? Deck. You can make it 6 or 7 or no, not 7, because that's an off. So
And 8 for 10.
let's just make it 8.
8?
I don't know why, but let's just make it 8. Guys, the last one on the page where it says 1 hydroxy, could we make it 8 hydroxy? Because yeah, 1's not possible. Yeah. Does anybody want to go and draw? Draw one, which is.
I'll draw the simplest one.
What's wrong? Cool. Good. Next one.
Anyone else?
I'll do the next one. I'm not sure.
We're changing, this is impossible. We're going 8 hydroxy.
No?
It said
It's not cyclo.
it said pentane.
Does it say cyclopentane anywhere?
Oh.
No.
Never mind. Okay, you go.
Is it methyl or methoxy?
Methoxy. It's methoxy.
What would that be like?
Oh,
Is that methoxy or not?
yeah, that's it. Methoxy, 1 carbon with an O.
What do you think?
What do you think, Mar?
Yeah. I mean, if I give you that structure, would you call that methoxy? No, you're right.
But what about?
What about what?
Oh, because no, never mind. Hetoxy. I was okay.
There's also an error in the naming, it's supposed to be easy.
Oh, I didn't include that.
Oh.
So if the name doesn't include, then you can draw either, because the name is not stereo specific, so
Oh,
your
okay.
drawing doesn't have to be stereo
Oh, okay.
specific. Just like, you know, how the structure, like for example, this is not a stereo specific drawing, because we are not showing wedges, dashes and all of that stuff, so then your name does not have to include that.
Okay.
Similarly, if the name doesn't include it, you can draw it.
Thank you.
Yeah. Okay, guys, do these look okay? Everybody okay?
Yeah.
Questions about naming carboxylic acids? Okay, then let's talk a little bit more about carboxylic acids. We will get to the naming of families a bit later, so hold on to that worksheet because we will get to it later once we've looked into carboxylic acids a little bit more. Sorry, I was looking at something. Okay, yeah. So, we have seen carboxylic acids before, first quarter, when we were learning about acids and bases. So, in general, would you expect carboxylic acids to be acids or bases? Name, right? Acids. So let's talk about acidity. of carboxylic acids. Now, they're not very strong acids. Typically speaking, organic acids are way weaker than inorganic acids, also known as mineral acids. HCl, sulfuric acid, nitric acid, blah, blah. Those are all inorganic acids. They are way stronger acids than organic acids are. Typically, carboxylic acids compared to the inorganic acids are much weaker acids. But within the organic world, they are our acids, within the organic category. Typically speaking, a carboxylic acid pKa, typically speaking, is around 4 to 5, is that generally speaking their pKa values. So as you can see, they're not very strong acids, especially if you're going to compare them with things like sulfuric or nitric or hydrochloric and all of those things that we are more familiar with. Those are way stronger. Benzoic acid, I'm trying to remember. Benzoic acid pKa is, does anybody have their pKa tables?
Yeah, I do.
Trying to remember. I think,
pKa tables are.
does anybody,
It's right here.
can someone tell me what is the pKa, thank you, of benzoic acid? That's it should be here. Oh, yeah, 4.2. So same thing, around the same range, 4 to 5 pKa is what values that they are all in. So not very strong, but for organic people, that is strong. Can you tell me which is stronger acid? An alcohol or a carboxylic acid? Which is a stronger acid? And why? Which would be a stronger acid?
Well,
An alcohol or
I would
carboxylic,
say
without looking at pKa's?
I would say carboxylic
Why?
acid because it's the highest acidity.
Resonance?
Why?
Oh, but
Resonance?
Of what?
the conjugate.
Conjugate base. You gotta go
Resonance
to
of
the
the
conjugate
conjugate
base.
base.
What is the conjugate base of an alcohol?
An alkoxide.
What is the conjugate base of a carboxylic acid?
A carboxylate.
Carboxylate. Exactly. Which of these is more stable?
The second one,
Why is the carboxylate, it's called carboxylate?
because it can jump around with resonance.
Hopefully you won't say that in the answer. When you're saying it, what is the it?
The negative charge on the oxygen can go down from a
Can be
double bond.
delocalized,
That's
can
the
be
word.
spread around, can be dispersed, not jump around. Spread.
So we need to change jump around for localize.
Delocalize.
Delocalize.
So more stable, right?
Mm-hmm.
So which is a stronger acid therefore?
Carboxylic
Absolutely.
acid.
That is the reason why alcohol's pKa's are around 15 or so, whereas their pKa's are around 4 and 5. So that is the reason why carboxylic acids are stronger acids. Okay, cool. Let me draw a few structures for you. The question is arrange in increasing order of acid strength. So when you're discussing acidity, please look at the structures of the conjugate bases. The more stable conjugate base comes from the stronger acid. So if the question were, okay, these are all carboxylic acids, but we need to arrange them in increasing order of acidity. By the way, can someone tell me what's the IUPAC name of this carboxylic acid, which is commonly known as acetic acid? This is acetic acid. But what is its IUPAC name?
Ethanoic acid.
Exactly. Acetic acid is not an IUPAC name, but that's what we call it because we are so used to it. Its IUPAC name is ethanoic acid. Same thing though. FYI. Anyways, so we have these three carboxylic acids. Let's arrange them in increasing order of acid strength. While you're working on this, I'll draw a couple more here. Anybody? Do we have the answer for here? What's going to be number one?
The least acid strength.
So which one? Ethanoic, it's ethanoic.
Ethanoic
You
acid.
mean this guy?
Yes, yes.
Do you all agree?
Yes. Well,
Weakest of the four. Okay, what's number two then?
the left,
Weakest acid.
Okay.
the left one.
You
Cl.
mean 2-chloroethanoic acid?
Yes.
Is that what you're referring
That's
to?
exactly what I was.
That's what you were thinking, right?
Chloroacetic.
Do you all agree?
Yep.
Next one,
Dichloroethanoic.
to 2-dichloroethanoic acid. Agreed?
Yes.
And therefore most acidic? Everybody agrees?
2,2,2
And
trichloroethanoic
will you
acid.
be able to write a good explanation?
No.
Oh, come on. Why not?
Inductive effect.
Yes? Everybody understands though why?
Just
I
the,
see some heads shaking, the others are just staring at me.
Just
So I'm
like the
okay, I don't know what to
explanation.
do. Oh, come on.
In case I didn't
You
know.
just didn't want,
Just to make sure we have.
draw
it
out
right.
the conjugate base, okay? Draw out the conjugate base. Let's say this is a question on the exam. What are you gonna do? This is what I expect to see.
Draw a
Draw out the
conjugate basis.
conjugate basis. Please go ahead. Draw it out.
Up there?
No, or paper, your paper. It's okay. So let's draw it out. Agreed? Is everybody okay with that? Okay, now once you've drawn this, guys, have you guys heard this saying? A picture speaks more than 1,000 words.
yes.
What you can say in a drawing is way more clearer than if you were to write it, especially if I were to talk about writing skills these days. I'm old. I come from the time when there was huge emphasis on writing, but now we don't do that as much anymore. So pictures, drawings tell so much more. Okay, now that we have those structures, which of these is the most stable conjugate base?
4.
Why is that the most stable conjugate base?
Because the chlorines are very electronegative, so they're gonna pull electrons close. Yeah.
They are electronegative, they will pull electron density in the sigma bonds towards themselves. What is that called?
Inductive effect.
Inductive effect. 3 chlorines are pulling that negative charge away from oxygen via inductive effect. Agreed?
Mm-hmm.
Which will stabilize. What will that do to the negative charge? If you are negative and I'm taking electron density
Positive.
away from you, what is that going to do to you? Will it stabilize you, destabilize you, or leave you as is? Stabilize.
Mm-hmm.
So that is stabilizing the negative charge. Okay, which is the least stable conjugate base of the 4.
Ethanoate.
Because there is no chlorine to stabilize the negative charge due to inductive effect from the chlorines, because there's no chlorine. Agreed?
Mm-hmm.
So therefore, and of course, this is somewhat more stable than the least stable, and this one is somewhat more less stable than the most stable because of the number of chlorines. So therefore, which is the strongest acid? Number 4, because it creates the most stable conjugate base, which is the least acidic compound. Acetic acid, because it creates the least stable conjugate base. Does that make sense? Everybody got it? Yeah? Okay, what about that one?
The third one.
Yeah. What do you want to call it? Weakest? Okay, and then number 2 and number 3, the left, the only one left. You all agree?
Yeah.
Mm-hmm.
Because again, that's an electron donating group. So what is that going to do to the conjugate base?
Pull it.
That's an electron donating group.
It's gonna give electron density.
Pour, like,
So once you
throw
get a
electrons
negative
into
charge, what will that do to the negative charge?
make it even more negative.
So is that stabilizing, destabilizing?
Destabilizing.
Exactly. What about the nitro group? It is an electron.
Withdrawing
So
group.
what does that do to the conjugate base? Stabilize it by pulling the electron density away from the oxygen. Does that make sense, everybody? Okay, last one, which is kind of the same as the first one. Which one is number 1? This one? Propanoic. 1, 2, 3, propanoic, right?
Okay.
Is that what you're talking about?
Yeah, but then I started thinking about it, I was ready now.
Agree?
Yeah.
What's 2?
The. Oh.
Same thing, but fluorine is the
2-fluoropropanoic acid. Why is the 2-fluoropropanoic acid is a stronger acid than 2-chloropropanoic acid?
Isn't it bigger or more electronegative?
Bigger or more electronegative? Can't be both. More electronegative, so its inductive effect is way stronger than the inductive effect of chlorine is. Agreed. So you got to explain from that all of that perspective. Okay, what comes next? What's 3?
2-fluoropropanoate.
And why is
propanoic
that
acid.
more acidic than 2?
Closer to the.
Closer.
Fluorine is
Inductive
closer.
effect is about distance. Inductive effect gets weaker if things get farther away from each other. Resonance, that has 0 effect, but inductive effect depends on that. And then of course this, because it has 2 fluorines in that position. Does everybody agree?
Mhm.
So it's all about stabilizing the conjugate base. You got to draw the structure and explain from that point of view. Okay, what I need you guys to do here, because we've done it last time, so hopefully you remember. Can you please tell me very quickly, guys, let's not spend too much time on things that shouldn't take that much time. Please tell me what would be the products. And I'm going to write something similar for phenol. Same, so please, the products. And I remember we did this in, of course, I think sometime in October last year.
Mm-hmm.
But when we discussed acids and bases, but I need you to draw for me, tell me what the products would be during these acid-base reactions. So that's carboxylic acid, that's phenol, one more, let's say, an alcohol, some alcohol, whichever. Then why am I doing this? Because, okay, let me not do this.
I don't even remember, to be honest.
Okay. So this is two common bases used in the lab, sodium bicarbonate, sodium hydroxide. That's for phenols, that's for alcohols. I need you to tell me what the products would be. Can you please tell me what would the product be in this case?
So you're both gonna take a
Carboxylate
Carboxylate and what
Plus-
else?
carbonic acid.
And what, okay, carbonic acid for that. Do you all agree?
Mm-hmm.
What about here?
The carboxylate
Same
plus
thing.
plus water.
Plus water. Here's what I want you to do, please. Because again, which is the acid in these reactions? On the reactant side, which is the acid?
The carboxylic
Do you guys
acid.
agree?
Yep.
What are their pKa's? Generally between 4 and 5.
Mm-hmm.
What's the acid in the first equation on the product side?
First acid,
What's the acid in the product side for the first equation?
carbonic acid.
Okay, what's the acid on the product side for the second equation?
Water.
Can you please tell me what the pKa's are? Fish out the pKa table. Tell me what are the pKa's, please.
pKa table. In the pKa?
Water is around 15 something, right?
Water is 15.7.
7, is it 7?
Yeah,
Okay.
15.7.
Okay. Carbonic acid, if anybody has it ready, just let us know so we don't have to spend too much time.
Come on.
Anybody have carbonic acid? You just Google searched it.
No Google
What did you
searching.
say?
6.37. Siri says
6.4.
Okay, so let's just say fine, 6.4, 6.37 rounded to 6.4. Everybody okay? Here's the question I have for you. With those pKa values, can you tell me in which direction would this equilibrium be? Will it be in the direction of the products or the reactants?
Reactants.
Calm, slow down, think about it, then tell me. When carboxylic acids react with sodium bicarbonate, will the equilibrium be in the direction of the products or reactants? What's the rule?
Higher pKa, weakest acid.
Okay, but then which direction does the equilibrium go?
Weakest acid.
So which is the weaker acid of the two in the first equation? Is the carboxylic acid the weaker acid or carbonic acid the weaker acid?
Carbonic.
So which direction is the equilibrium in?
Right.
Right? How about the second equation?
Here's the reactant.
Slow down. Slow down.
Goes to the right again.
Equilibrium is in an acid-base reaction. Equilibrium is in the direction of the weaker acid. Weaker acid means higher pKa. So which direction does this equilibrium go?
Right.
What does that mean? It means that if you want to neutralize a carboxylic acid, you can use either of the base, they both will work. Agreed? Yes?
Yep.
Did it make sense?
Yes.
So now I want you to do the rest for me. The question is, you got to finish the equations, both phenol and alcohol. You got to figure out the pKa's and tell me which is a good base to deprotonate a phenol, and would any of these be a good base to deprotonate an alcohol? Please do the analysis on your own for phenol and alcohols and tell me which base would be good to use. For carboxylic acid, we can use either because both sodium bicarbonate and sodium hydroxide will push the equilibrium in the direction we want. Is it the same with phenols? Is it the same with alcohols?
Just as a
What?
reminder, equilibrium favors the weaker acid.
Equilibrium favors the weaker acid.
Yep.
So if you do the exact same analysis, but this time for a phenol, would both bases work? Or is one not going to be a good idea? What about alcohol? Same thing. What? Sorry.
Oh, I thought you were asking.
Yeah, I am.
Oh, for the phenol, the NaOH will be better
Why?
because the pKa of phenol is about 10. So if you do it with the top one, it's gonna move the reaction towards the product side.
Phenol pKa
Reaction side,
is 10.
yes.
pKa of carbonic acid is, what was it, 6.4. That's a stronger acid than phenol. This equilibrium actually is in the direction of the reactant. Sodium bicarbonate not work with phenols. It's not a strong enough acid to deprotonate a phenol. Do you guys see that?
Mm-hmm.
That's not going to work. What about NaOH? Water pKa is 15.7. So which direction is this equilibrium in?
Goes towards the right.
So that's a good. So please notice the difference. If you have a carboxylic acid, you can use either. Great. But if you have a phenol, sodium bicarb won't work. Sodium hydroxide will do great. What about alcohols? What are their general pKas? Approximately 15 to 16. Same thing. I'm not drawing the whole thing, but it creates carbonic acid as the byproduct and water. Carbonic acid pKa is 6.4. This is about 15.7. So on and so forth. Will either of them work?
No.
Neither of them will work. Neither of them, and we've talked about this when we were studying alcohols, that if you had to deprotonate an alcohol, this would work. That's why we need way stronger bases to deprotonate an alcohol, if you remember. But do you guys see that analysis?
Mm-hmm.
So if you have something like this to analyze, you should be able to. You should be able to write the products, you should be able to look up pKas and then decide which direction is that equilibrium in, and yes, is this a good idea or not a good idea? Does everyone understand this? Questions? Please remember, in acid-base reactions, equilibrium is always in the direction of the weaker acid. Always. Okay, so that's the acidity of carboxylic acids. Let's talk about synthesis of carboxylic acids. Most of these reactions we've already seen in previous chapters actually. There's only one that is new. Everything else we've seen before. So let's summarize them and then we'll look at a new one. And actually we'll be doing that in lab next week. So, isn't that lab next week?
Mm-hmm.
I forgot.
Yeah.
Is it the
Okay.
benzoate?
Methyl salicylate.
So, carboxylic acids, can you guys remind me some ways of making carboxylic acids that we have seen before? What do we make them out of? Yeah.
Aldehydes.
Aldehydes, okay. Aldehydes, oh, I didn't, okay, fine. Yes, absolutely. What will you use?
The CR03.
CR, there are a bunch of options here. CR, chromium trioxide with an acid.
You could also
or-
use PCC.
PCC, no, that's a weak oxidant.
MC.
Oh, no,
PDA.
no, I'm sorry, yeah, no. That
Right,
was
or you can use sodium dichromate
with H2SO4.
with sulfuric acid, or we also saw something today.
MCPBA.
MC, you can even do that. You'll get a carboxylic acid, right? Okay,
Mhm.
what else can we make a carboxylic acid from?
Come on.
That's up.
Carboxylic acid.
What were you saying?
No, I'm looking at that.
Mm,
How about a primary alcohol?
Oh, yes.
Actually, I'm gonna write it there.
What was it on?
Because primary alcohol first makes this and then, right? So if I wanted to convert a primary alcohol into carboxylic acid, do I use a weak oxidizing agent or a strong oxidizing agent?
Strong oxidizing agent.
Absolutely. What else?
Ozonolysis.
Of what?
Ozonolysis of an alkyne.
Alkyne. Alkynes can be ozonalized to create carboxylic acids or acetic acid, or I think water also goes there. Okay, what else?
the KMNO4,
But what is the reactant?
C, and an H.
Alkene.
An alkene? Oh, I see, okay, yeah, is that what you're thinking
Yeah.
about? But then it has to be an alkene that has at least one hydrogen on there. If none of these are, if they're all R's, then you just get a ketone and you'll stop.
Mm.
So you have to have hydrogens there. Okay, so then you're using a strong oxidizing agent, KMNO4, in presence of a base. But then you also have to then acidify it, otherwise you just get carboxylate,
Yeah.
not carboxylic acid. Oops, you have to acidify it.
There could be just one H on one side, right?
Yes, but then only that will become a carboxylic,
Yeah.
other will be a ketone.
Yeah.
Yes, what else? One more method that we've done already. How about if you have an alkyl benzene?
Oh,
Can
an alkyl benzene, and we use KMNO4.
Either KMNO4 with this or sodium dichromate can be, the R can become benzoic acid, right?
Mhm.
Except which? Except
T-butyl.
R, if R is T-butyl, that doesn't react. Everybody
Oh.
remember
Oh,
that?
yeah, yeah, yeah.
So this we've already seen. There are two new ways of making making a carboxylic acid. One is using Grignard reagent. This is the one we'll be doing in lab. Next lab, we will be carboxylating a Grignard, and that's one of the reactions of you guys' project as well. You're carboxylating a Grignard. So a Grignard can be reacted with carbon dioxide. Can someone quickly tell me what's the structure of carbon dioxide? Hopefully within, sorry, one more time.
Sorry, C double bonded with 2 oxygen.
Exactly.
2C double bond O's.
And followed by, that's what we'll be doing in lab next week. There's another new way of making a carboxylic acid, which is actually why nitriles are considered to be derivatives of carboxylic acids, because they can be hydrolyzed. We'll look at the mechanism later by using either dilute acid or dilute base. Nitrile becomes a carboxylic acid. So this portion is this portion right here. What happens to nitrogen? When we look at the mechanism, we'll go over all of those details. But let's look at the carboxylation part. How does that work? So this is what you are doing in lab next week. You are carboxylating phenyl magnesium bromide.
We're not making the green.
Unfortunately, time. Making the Grignard can sometimes take time, and we may not have that. So unfortunate. So the choice is, so where, what mechanism, what do you think is the first step?
The nucleophile attacks.
Where's the nucleophile?
Oh, sorry.
Or rather, what is the nucleophile?
The phenol,
And attacks where?
the carbon.
Exactly. You have a C double bond O.
Mhm.
Just like what you've seen in other reactions, the nucleophile phenyl from the Grignard attacks the electrophilic carbon with the double bond O. What does that create?
O minus C double bond O with 10.
What is that? That's a carboxylate.
Mm-hmm.
What do we have to do to the carboxylate to make it carboxylic acid?
Pronate it.
And you're done. So carboxylating Grignards to create carboxylic acid is a very quick way of creating carboxylic acids. Where does the Grignard come from, anybody?
Reacting benzene with,
No.
bromobenzene
So
with magnesium.
right? Either in this case, but alkyl halide reacting with magnesium creates Grignard, you carboxylate it. Make sense, everybody?
Did it react twice?
With what?
Oh, wait, never mind.
No, I wanna know, with what? Are you thinking
I
about?
realize neither of them are good leading groups, so it couldn't leave. If another phenol attack
Mm.
would leave.
There isn't, yeah. Where was I going with it? I was going somewhere. Okay, cool. Let's look at some more examples.
Let's just go into it.
Sure, yeah. Why the double bond?
The double.
Oh, wait, sorry.
Sure?
Yes.
You get it, right?
Yeah, because
HBr,
takes it
exactly.
and yeah.
So guys, please notice, when you create a carboxylic acid, you're adding a carbon. Originally, we had 7 carbons, but we are adding a carbon. Do you notice that?
Mm-hmm.
1 carbon got added. So when you make a carboxylic acid using nitriles, we are adding a carbon. When you make a carboxylic acid using Grignards, we are adding a carbon. 1 carbon gets introduced through carbon dioxide. Okay, cool. Next one. And we'll stop there. We'll do rest on Monday. Quiz on Monday will cover through synthesis of carboxylic acids, I guess. Please, let's write those answers as well. Can I erase this?
Yes.
Yeah, no, it's, I'm fine. So it will cover all everything till right?
Till today, yeah. Through today. Go on, go on. Go
Okay.
on, go ahead. Ignore them. In a good way, just finish.
We'll figure out later.
Oh, okay. Anybody for the last one? Annika, are you getting up to go? No? Okay.
Let me draw it out. Tert-butyl-benzene.
Vivian, Annika, and Mayas, just a quick word for you all. I have your exams, I totally forgot. See, I did put it. You said you had a reminder email. I don't want to forget. No.
Yeah.
Cam-104.
Okay, you guys can think about it, tell me Monday, but, oh. Okay, but that's not the final product,
Yeah.
that's just the first step.
Yeah.
That's just the first.
So what will happen second, third, and fourth steps?
Thank you, Sumita. Thank you, Sumita.
Thank
Okay. Quiz on Monday will cover through synthesis of, since nobody is leaving, because you love Ochem, what's going on here?
The C double bond O is taken out.
What's going on 3 and 4? Nope.
Benzoic acid.
T-butyl is not affected.
So
The
we
other
had-
R just gets broken off, becomes carboxylic acid, so that's your final.
So we had to introduce another R group in order to get the carboxylic acid.
Exactly.
That was the goal of this reaction.
But please notice that dash showed the first product with the para position, because that's a ortho-para director, but it blocks the ortho position, so the electrophile goes to the para position. Okay, cool. So I was looking at the procedure last night. It seemed deceptively simple. So let's see. No, not because, it just feels like, is it really that easy? Because that's a good thing, right, if it works. I think we can do first 3 steps in one day, because the Friedel-Crafts acylation may be a little bit time to set up, 45 minutes at 0 degrees, and then work up. I think we can finish it in 2 to 3 hours max. But the other 2 are just mix, stir, and you're done kind of steps, it feels like. In fact, they were doing it in a separatory funnel. I'm like, I don't like that, that makes me scared. The point is, I feel like we might be able to do first, second, third step on Friday in one day. Is that doable, or do you guys have a time limit that you can say? I'm not going to, not more than 4 p.m. even I don't, actually. I have another meeting from 2 to 3, so we'll figure it out. The point is, it's doable. And then the Grignard part, where you're making the Grignard and then react it, and then carboxylating it, the dry ice part, we can probably do it the following Friday.
Oh, I think
Maybe. We'll see how things go. Is that okay?
Wait, so we're doing our,
Full video.
We were gonna ask about, we have a field trip for biology next week on Friday. And 2 of wanna go? Friday?
I'm kinda like,
Where are you guys going? Where? Oh. You guys decide. I have set aside May 2nd, May 9th, and what's after 16th for mostly you guys. And because you guys were coming, I said yes to another bio group, otherwise